Okay, so now let's check our understanding with this second problem. So how many moles of hydrogen gas are required to react completely with 2 moles of carbon monoxide? And here, according to this reaction, uh, that's described below. So how many grams of H2 are required? So we're going to answer two questions. How many moles and how many grams are required to react with 2 moles of carbon monoxide? Okay? So this is pretty much industrially how we make methanol. Um, but nowadays, I think we're looking towards using CO2, so that we can take the CO2 that we produce in the air and then convert it to methanol, which is a very important chemical in the chemical industry. Okay, so if we look at our balanced chemical equation, we should put ones in front of the terms that don't have a 1, just so we know that there's a 1 in front there. Okay, so our mole ratios are either 1 mole CO to 2 moles hydrogen, or 2 moles hydrogen to 1 mole CO. So if you use the wrong mole ratio in your calculation, you should notice that your units that you end up with won't make sense. So if you end up with a mole of CO at the end and you used mole CO in the beginning, you know that that's the wrong fraction. We don't want to use that. Okay, so let's begin here. So we have 2 moles. So we start out with 2 moles. So let's highlight 2 moles here. Okay, so let's highlight these 2 moles here. So we see here we have 2 moles of CO, right? So we want to highlight that. But let me see if I can make this a little bit easier to see. There we go. So 2 moles of CO. So that's an important piece of information. So we want to keep that in the back of our minds, or at the front of our minds, sorry. So 2 moles CO, so that's what we start with, right? Okay? So we know that for every mole of CO, we produce moles of hydrogen. So at the end, we want moles of hydrogen here. So the only way, sorry, I should put a 2 here so we don't get confused. So for every, so the equation that has mole of hydrogens as the numerator is the second one we wrote, the 2 moles over 1 mole of CO. So we're going to use that one. So let's do our train track method here. 2 mole H2, 1 mole CO. Okay, the mole COs will cancel out, and we just multiply 2 times 2, we get 4 moles of H2. So that's how many moles of hydrogen we produce. So that'll be our first answer. Now, how many grams are required? So let's write the molar masses here. So H2, the molar mass is equal to the molar mass of hydrogen times 2, right? So that's going to be 1.008. So I may use 1.008 or 1.01 for hydrogen's molar mass, but it doesn't matter. You could use 1.01. The answer would just be slightly different, but not by much. So it's okay. It's a good approximation. Times 2, which equals, oh, let's put the equal, let's write it down here below here, equals 2.016 grams, okay, per mole. All right, so there we go. So that's our molar mass. So keep that somewhere on the page so you know that's the molar mass. So never try to do these in your head when you're just doing these things. It can be kind of tricky. So now we take 4 moles H2 4 moles H2 times, or sorry, we could just use the train track method again, so it's easier to visualize here. So we know now that for every mole of H2, we get 2.016 grams of hydrogen here. So if we multiply that, since there's only one sig fig in the amount of moles in that we were given, we should only list this to one sig fig. But we can write it out as we can write out the full number here. Maybe that'll be more helpful. 0.16 times 4, we get 8.0064 grams. But we want to round to sig figs, right? So we're going to underline the first significant digit, because that's only one sig fig. And we're going to round this off to 8 grams. So approximately 8 grams of hydrogen. So we do this because we don't know the accuracy of which we measured the number 2 for 2 moles of CO. So the only appropriate answer we can give at the end is 8 grams. We can't say, oh, there's 8.0 grams, because we don't know any certainty past the decimal point, because there's no decimal point in the first value. There's only one significant figure, and it turns out that's also the most uncertain value, because there's only one sig fig. So we can only know up to a certain point that it's 2 or one significant figure. So that's why we list it as 8. Okay. So I thought I'd go over sig figs for the beginning of this course, just so we can refresh it in our minds for students who may need it. All right. So that's 8 grams. So on every chemistry exam, you should circle your answer so I know where to look on the page. If it's not clear to me, and a ambiguous answer is also a wrong answer. So I learned that a lot in grad school. So because we grade a lot of exams in grad school, and it's important that when you provide an answer that it's clear, concise, and gets to the point. And you're not just drawing a bunch of answers on the page. So we need to know where to look. So if you circle your answer, that you'll be in our good graces. Okay? So and it'll help demonstrate that you know how to do the you understood how to do the problem too. So that will be helpful. All right, there we go. Okay, so now let's go to the second part of this question here. How many hydrogen molecules would be needed to consume 2 moles of carbon monoxide? How many H atoms would be needed? Okay, so this one, we need to take it a little step further. So we determined that we have 4 moles of hydrogen, right? So now we need to convert that not to grams, but to molecules. So we want to figure out how many molecules. So we need to represent how many molecules are in 4 moles of hydrogen, which is in 8 grams of hydrogen. We want to figure the total number of molecules. Okay, so it's probably going to be a big number if we have 4 moles of it. So this is where we use what we call Na, or Avogadro's number. So 4 moles H2. Okay, so 4 moles of hydrogen. So how many molecules will we need? Well, we will need to use Avogadro's number. So let's just remind ourselves that Avogadro's number, Na, equals 0.022 times 10 to the 23rd per mole. So every mole will have this many number or units of another unit. So for example, if we're trying to find a mole of things, so a mole of hydrogen atoms will have this many moles of hydrogen atoms. So in this case, we're going to have 6.022 times 10 to the 23rd. So let's just use our box method here. We're going to say H2 molecules. So it doesn't mean moles, but H2 molecules per 1 mole of H2. Okay? And then we get a very large number. We're going to get 2.4 times 10 to the 24th. So if we input in our calculator, that's what we get, H2 molecules. So be sure to know how to do this calculation in your calculators. So you would put 4, so you would type 4 times, so times key, 6.022, type the EE button, so EE button, and you're going to put 23 as the value, then press, then hit enter, and it should give you a number, which is this number right here. Okay, so this number right there, that should give you your number in the calculator. Okay, all right. So now we have to figure out how many hydrogen atoms would be needed. So how many hydrogen atoms would be included in this number of molecules of H2? And for this case, we just chose 2.4 molecules. I think we want at least 1 digit hexadecimal. That's why I chose 2. But you can also put 2 times 10 to the 24th. That would be perfectly acceptable too. But now we have 2.4. 2.4 times 10 to the 24th. H2 molecules. And we know just based on the formula that that there's 2 hydrogen atoms, so 2 H atoms per 1 H2 molecule. So our value here will simply be double of what we started with times 2. So we get 4.8 times 10 to the 24th H atoms, so hydrogen atoms. So that's how we would answer that question using both Avogadro's number and the chemical formula for H2 molecule to determine how many hydrogen atoms there are. Okay. So that's another part of stoichiometry. We may ask you how many molecules there are, and there are some problems like this in the first homework assignment. So you'll get more practice with that. So refer back to this example on how to set it up for the homework. Okay, so let's move on here. So let's do another exercise here. Calculate the number of grams of ammonia needed to prepare 3 grams of nitrogen oxide when it burns in the presence of excess oxygen. Okay, so we need to know what the compound that we know the mass of. So that it will be nitrogen oxide. So let's just write it out here: nitrogen oxide. I write it out because if I simply put NO, people may interpret that as no. So I want to make sure that we're perfectly clear. So nitrogen oxide, NO. Okay? All right. Now let's calculate the molar mass of NO and convert it to moles. Let's convert the molecule, the mass of nitrogen oxide to moles. So the molar mass of nitrogen oxide, we have 14. Let's just put 0.01 grams per mole for nitrogen plus, so this will be for nitrogen here. and then 16.00 for oxygen. And so we get 30.01 grams nitrogen oxide per mole of nitrogen oxide. Okay? So then we could set up this as a ratio. We get 30.01 grams of nitrogen oxide for 1 mole. Oh, sorry, I got it backwards. See? So we need to go over first what we want. So we want, in this value here, we want moles of NO. So at the top here, we're going to put 1 mole of nitrogen oxide is going to require that we know the molar mass. And so for 1 mole, we're going to get 30.01 grams of nitrogen oxide. Like that. Okay, so we do the math here is about 110. So we're going to say 0.100 moles of nitrogen oxide. And you see here we stopped at 3 sig figs because the mass of nitrogen oxide is only in 3 sig figs. So that's going to limit our answer to 3 significant figures. Okay. So that's how we convert from mass to moles. So now let's go back to the chemical equation here, and we see that our ratio is, for ammonia, we have 4 moles of ammonia for every 4 moles of nitrogen oxide produced. So they're in a 1-to-1 ratio. So when everything's in the 1-to-1 ratio, you can assume that the moles of nitrogen oxide is going to equal the moles of ammonia that was consumed. Okay? So in this case, we notice that for 4 moles of ammonia, we get 4 moles of nitrogen oxide. So I'm just going to say the names all the time because if I say something like NO, people will not understand what I mean. So I'm just going to say the names like every time, we do these kind of examples. Okay, so we have that example, and then we have also 4 moles of nitrogen oxide, gives us 4 moles of ammonia. Okay? All right. Or we could simply write this as 1 mole ammonia. We could simplify it to 1 mole nitrogen oxide. And then 1 mole nitrogen oxide to 1 mole ammonia. Okay, so you can simplify it if you'd like. So using our mole ratio, let's convert moles of nitrogen oxide to the moles of ammonia. So we're going to take our value in the previous step 2, 0.100 moles of nitrogen oxide. And the ratio we're going to use is we want ammonia, right? So let's write out what we want. We want ammonia. So ammonia should be the numerator in this case. So we're going to pick 1 mole ammonia for 1 mole of nitrogen oxide. So here, nitrogen oxide will cancel out. So we get an equivalent of 0.100 mole of ammonia. So there we go. So that's how we would convert from grams of nitrogen oxide to moles of ammonia. So now we need to go to the last part where we want to figure out grams, because usually in order to measure out a known molar amount, you need to convert it to grams, so something we can actually measure out. So you can't actually measure out moles directly. You need to convert it to grams, and that gram equivalent would equal 0.1 mole. So that's how we measure things out in the lab. So ammonia's molar mass, we have 3 times 1.01 plus, so this is for hydrogen, plus 14.01, that's for nitrogen, and then we get a value of, all right, so let me just double check here. Okay, so we get 3.03 plus 14.01, and we get 17.04. So we get 17.04 grams per mole for ammonia. Okay? So that's our molar mass. So now we take the moles of ammonia here that we calculated previously, 0.100. So my suggestion when doing these problems, you do it in a stepwise manner. Because if you try to think about doing the whole problem in like a single step, it may get confusing, and you may students may skip a step when they shouldn't have. And so it's important that you do these problems, you do it kind of stepwise as you're learning it, and then as you get better at it, you can set up the problems easier and just solve them directly. Okay, so it's important that we do these steps for when we're learning these things, and then how you ever do a math problem. First, you follow the teacher's example how to do the math problem, and then you get the hang of it, and then mentally you can do it more in your head on an exam or for homework. Okay, so 0.100 moles ammonia. So we know our molar mass is 1 mole ammonia, because we want grams, right? So we want to put grams on the top here. 17.04 grams ammonia. And if we multiply that through, we get 1.70 grams of ammonia. Okay, so that's how we would do this calculation. So let's double check here. 0.1 times 17.04. And we get around 1.70 grams of ammonia, and that's our final answer. So let's just circle our answer here, just so we know it's our final answer, and that's how we do stoichiometry. Okay, so let's end this video here, and I'll see you in the next one.